So now that we know a little bit about functions, let's start talking about some specific functions, namely the difference between linear and nonlinear functions. So if you take a look at the word linear, it's got some words in it like ear, near, in, are, like a pirate. But the main word it has in it is line, and that's what linear means. Linear is a function that graphs a straight line. Now, all lines are straight, so linear again means line. Nonlinear means, well, it's not a line, which means it could be some kind of curve. So what we know about linear functions is this. When we talk about linear functions are equations like f of x is equal to 7x plus 5. This is linear. Now, why is it linear? Because its biggest power is x to the first. You'll notice in here we have just an x. So that makes it linear. Now, another example is g of x is equal to something like 4. Well, the differences between these functions both make lines. This first one, f of x, makes a line that looks like this. It's more diagonal, where g of x equals 4 just makes a horizontal line. But the difference between these functions that are linear and functions that are not linear, well, is this. I'll show you a nonlinear function. H of x is equal to, let's do 7x squared plus x. And you'll notice its biggest power is now x to the second. This is not a linear function. Here's another example. I of x is equal to 9 to the x power. Well, here the power is x, and there's no x to the first in here. So these are examples of nonlinear functions. As you move into more math later on, you'll start to experience a lot more nonlinear functions. But mainly for a lot of the things we're going to do in this course, we're going to focus on things that are linear. And at the end of the course, we'll focus on things that are indeed x squared, which make what's known as a parabola. Now, from time to time, we're also going to talk about these words discrete and continuous. Discrete means we've got a domain made up of separated or disconnected values. For example, discrete might have a graph that looks a little something like this. It's still a function, but you've got mainly just points all over the place where nothing's connected. Continuous means we're dealing with a domain where all the x values are values that we're going to use. And so continuous is just like taking my pen right now, just kind of making it flow, making the graph flow. And so we can have discrete or continuous functions that can be, well, linear or nonlinear, so don't get mixed up with those. So the main thing is know the difference between linear and nonlinear. Know that there's times where our domain might be discrete, which means we only want to work with certain numbers, or continuous, which means we want to work with all the numbers. I'll give you an example of discrete domain. We go to the store and buy a shirt. We buy one shirt, we buy two shirts, we buy three shirts, and so on. That's a discrete domain because we're only using domains of 1, 2, and 3, and so on. A continuous domain would be like going to the store and buying a 1 shirt or 1.1 shirts or 1.2 shirts or 1.3 shirts. We know that that doesn't make any sense, and so that's the reason for those two words. So next I want to show you how we can tell by looking at a table of values, a domain, the x, and the range for y, if our table represents something that's linear or nonlinear. Well, linear functions have to have some kind of pattern. And so look at the numbers between x. From 0 to 1, we're going up by 1. From 1 to 2, also up by 1. From 2 to 3, and from 3 to 4. Now you'll notice from the y values, from -5 to -2, we've got to go up 3 to get there. From -2 to 1, we've got to add 3 to get from -2 to 1. We also know 1 plus 3 is going to give us 4, and 4 plus 3 is going to give us 7. This is an example of a linear function. The domain is discrete because we're only using 0, 1, 2, 3, and 4. But what we notice is this, and you're going to see this phrase a lot, is we have a rate of change, and for change we sometimes use a triangle to show change. The rate of change is consistent, which means we're going up by the same amount each time. You'll notice if we put these as a fraction, we'd have 1/3, 1/3, 1/3, and 1/3 each time. Okay, consistent rate of change. Let's take a look at our second example. Our second example goes from 0 up to 4. And notice again we're going up by 1, so that's good. We're consistent there. It doesn't always have to be the case. But on the bottom here, we're going down by 1, which is okay to go down. But we're going down by 2, down by 4, down by 8. So this is an example of a nonlinear function. Now I want to show you this example just so you can kind of see a little bit different situation here. You'll notice on this table that I've just created that our x values are not consistent. We're going up by 1, going up by 2, going up by 4, and right there you might be thinking, well, it's not a function because we're not going up by the same amount each time. Well, on the surface it doesn't look like it's linear, but let's look a little deeper. Between 6 and 8, we're going up by 2. Between 8 and 12, we're going up by 4. 12 and 20, we're going up by 8. Man, there's nothing that looks linear at all. But remember, to be linear, we have to have something, a rate of change that's consistent. And so if you recall just a moment ago, we kind of made these into fractions. So here we've got this fraction where we're going up 1 on the x and 2 for the y, so that's a half. Here we're going up 2 between the x's and, well, 4 on the y's. And here we're going up 4 on the x's between 3 and 7. And from 12 to 20 we're going up by 8. So 4 eighths. Whoa. Look at all these fractions. They're all the same fractions. In fact, this is an example of a linear function. Still a discrete domain like the other two have been as well. But you'll notice the rate of change is the same between each ordered pair. Okay, and so that's unique, and so be on the lookout for those situations as well. So in closing on this concept, let's look at the independent practice, and we want to circle all the functions below that would be considered linear. So here's your hint. We're looking for functions where the biggest power of x is the first power, or anything that's equal to a constant. So take a look at these for just a moment and circle the ones you think would be linear, and then I'll come back and show you. Well, here we go. The first one, 3x plus 2, that's going to make a line because it's x to the first. As is the second one because it's x to the first, negative x. And remember, if there's no exponent on x, it's 1. Going to the right, x squared, not linear, it's x squared. 5 to the x on g of x, 5 to the x. The power, there is no x to the first in here other than in the exponent, so that's out. Going to the bottom row, h of x is out. I of x, it's equal to a constant 4. Negative 3x minus 6, that's linear. And the last one looks linear, but notice there's a negative x squared in there, so that makes it not linear. So in this video, you've learned a little bit about the differences between linear, which make a line and have a constant rate of change, and nonlinear functions, which, well, don't make a line and don't have a consistent rate of change.